All right. So we've just gone through the solution to exam 2, and I gave you the little pep talk about how you can do this. You know, like if you got a bad score on the exam, there's still plenty of points to be earned with the final. So a couple of other announcements here. Homework 6 is due on Friday, and the concepts included in homework 6 are up through the material that we covered on Friday. We're going to continue talking about primary treatment today, but the example I'm sharing with you in today's lecture doesn't have a corresponding homework problem in homework 6. Now this is out of left field, but apparently the State Department is looking to hire engineers, and that's not normally the case. I think normally they hire like political science type majors and so on, but I guess the U.S. government administers a lot of construction projects overseas and has to hire technical people to supervise how their money is being spent when aid is given to foreign governments. And so the State Department is looking to hire people in construction and engineering, and they're having an open house over in the Student Center on Wednesday from 2 to 3:30. And there's a guy who's spent most of his career as a diplomat, but I think he's also had some experience administering aid projects in foreign countries. And so if you're interested in an international career, that might be something worth stopping by to meet with him Wednesday, 2 to 3:30. And then, of course, I've announced this before, but if you're interested in learning more about the Corps of Engineers, they're having their free lunch on November 9th. Okay, so we're going to continue talking about primary treatment today. And the main aspect of what we're talking about today is scour velocity. So primary treatment is about settling particles to the bottom of the tank and floating particles, well, floating grease and liquids to the top. We don't have to calculate the speed of the grease movement upward because it's very fast. You know, oils separate from water in just a few moments. So there's no equations in our book that relate how fast that is. Although we'll take a look at some pictures today that illustrate how scum and grease can be collected off the top of the primary clarifier. But from a numerical perspective, what we've done before is we've had to calculate, number one, how quickly particles settle downward. And you know, with the exam, we were just looking at type 1 settling, which is assuming that the particles don't interact. In our last class period, we looked at some equations and did calculations related to type 2 settling. And do you remember what type 2 settling is called? Orthokinetic. And that's the phrase which means the particles are flocculating as they settle. So on Friday, we looked at what is the rate of settling when the particles are continuing to flocculate. Today, what we're going to look at is how quickly could we wipe the bottom of the settling basin and not disturb the particles that have settled. So we're going to be introducing scour, which is a negative thing here. We don't want to disturb that flock because we've just invested so much time and so much money to settle it to the bottom of the tank. Now we want to very gently wipe it towards a hopper and suck it out for sludge treatment. So the question is, how quickly can we move the hopper? And this formula for scour velocity is going to help us to estimate that. Once the particles are down at the bottom of the tank, then there are a few factors that contribute to how easily they're disrupted and lifted up off the bottom of the settling basin. This parameter beta, the dimensionless constant, which depends on whether the particles are interlocking or whether they're uniform granular particles that don't necessarily stick together in the same way that interlocking or sticky material would. So our text introduces a range of 0.04 to 0.06, which is relatively narrow range, but sometimes we just have to estimate based on either past experience or lab tests with the sludge, or maybe, you know, if you want to be conservative, you can assume that there isn't a lot of interlocking, and so that the scour velocity would be even lower if you use the low end of the range here. So scour velocity is how much velocity does it take to get those settled particles that are at the bottom like back up into the clarifier, which would be bad. You can see that there's the difference between the particle density and the liquid density. And so that's a driving force. And the more dense the particle is, the more resistant it will be to scour. And so later on when we're talking about secondary treatment, the particles are going to have a density that's much closer to water. Like the microorganisms in activated sludge are mostly water. And so the density of those microorganisms in the aeration basin is, I don't know, maybe like 1.1 or 1.05. But here in primary treatment, the particles still have quite a lot of clay particles, colloids, and so the density difference between the density of the particle and the density of the water is still pretty big, which is good for us. We can wipe down the primary clarifier a little bit more aggressively than we'd be able to with a secondary clarifier and not cause as much scour. You can see that the diameter of the particle is also going to be a factor, and the bigger the diameter of the particle, then the larger the scour velocity that can be tolerated. And then in the denominator of this formula is the Darcy-Weisbach friction factor. Now, for those of you who've already taken hydraulic engineering, you know that determining F is a lengthy and difficult process. You know, which friction factor to use depends on, in closed conduit flow, the diameter of the pipe, the temperature of the water, the velocity of the water. So picking a correct F value is not a trivial thing, but in a settling basin, the range of parameters would typically be between 0.02 and 0.03. Whereas in a pipe, we'd maybe see F values as low as 0.008 and as large as 0.0036. Settling basins don't have the same really wide distribution of velocities. You know, the velocities are low enough that we can key in on a typical range. Okay, so this again, this V scour is how much velocity does it take to disturb the flock and send it back up into the settling basin. So let's look at some pictures of what the settling basin looks like and some of the mechanical parts that are in there. This is a rectangular settling basin, and what you can see is that there's a chain-driven series of flights, as they're called, and that's a pretty fancy word for a wooden board, but it's just a wooden board on a chain, and the flights at the top of the tank are pushing the scum, which is largely oily materials that have risen to the top. But it can also include some organic materials that aren't oily. It could be, sometimes unfortunately, algae grows in a clarifier, so it could include like some plant-like stuff. At the bottom, the flights are scraping against the bottom of the tank. And so the question that we want to know is, how quickly should we run this chain-driven series of flights? Like, if this is scraping across the bottom, how fast should it be going? And if we know the velocity of these flights, then you know, what kind of motor should we get? How many RPMs? What should be the gear diameter? The example that I put together for today's class, I wanted it to be where we were solving for a rotational rate on the motor, but I ran out of time, so we're just going to calculate the velocity of the flight, and then gear diameters and sprocket lengths and so on we'll maybe have to leave for another day. Leave it for the final exam, just to spice things up. No, just kidding. We won't do that.
You're really excited about this final.
Oh, the final's going to be so hard. No, it's not. It's going to be the same as the other exams. In terms of,
All right.
which is to say super easy. So basically what we want to know is how quickly can these flights be dragged across the bottom of the tank? Because if they're moved too fast, then think about these particles are settling downward. But if this is moving really fast, then it's sending a bunch of swirls and turbulence into the settling basin. So at the top, the flights are pushing the oily scum towards a trough that the the water can flow over the top into that trough, or occasionally what they'll do is they'll tilt the trough and kind of squeegee the layer off the top into it. And you can get a sense for that here. There's these overflow pipes, and you can see that the scum layer is kind of accumulated here, and they can tilt the water. But the launders, that the effluent is actually going out of the clarifier, is on the other side of this concrete walkway. And the concrete walkway impinges down into the water because this is meant to be a barrier so that none of the scum will get into the launders. And so all of the scum should be intercepted by this slotted pipe drain. You can see that there's some foam at the top, and that used to be a real issue at wastewater treatment plants. The fact that detergents that were used through the 80s and the 70s and before that had a lot of phosphates in it. And when there was a lot of phosphates in detergents, it worked great for getting people's clothes and dishes clean, but it caused a lot of unpleasant and difficult foaming issues at treatment plants. And so luckily, phosphates have largely been banned in detergents, not just because of how it interferes with wastewater treatment plants, but also it contributed to algal blooms in the Gulf of Mexico. You've maybe heard of red tide before, which is when they have these big sections of the ocean that algae bloom and fish get killed and they start to decay, and it's because there's excess nutrients in wastewater that gets discharged into the Gulf of Mexico from the Mississippi River. So by limiting the amount of phosphate that gets into water, they've kind of reduced a lot of environmental problems, including foaming of wastewater at treatment plants. So here you can see the water going into the launders. It's relatively clear in appearance. The turbidity is less than it was when the wastewater came into the primary clarifier, but there's a little bit of foaming here, the froth that came from the phosphate that used to be in water. There are countries where phosphate isn't regulated as carefully as it is in the United States, and so if you do end up doing wastewater treatment plant for the State Department overseas, you might see some foam in a treatment plant. Sometimes you'll see foam in like hot tubs. It was always a gag when I was in college. There was a hot tub at our apartment complex, and people would always put soap in it just to, and they would get like 10 feet of foam. Kind of funny. But let's look at this scour velocity example and see if we can determine how quickly, this is a cross-sectional view, a side view of a rectangular clarifier. So if we had particles settling downward, there's supposed to be this quiescent zone where the particles aren't being interfered with, they're settling down, but then we have to get the sludge into a hopper and then suction it out. So to do that, the flights are traveling across the bottom of the tank, and they probably have some sort of a rubber seal on the leading edge to make sure that the particles are being wiped. But we want to know how quickly should those flights move. And the scour velocity, one pretty easy assumption for us to make is that as quickly as the flight is moving, then the water that's in contact with the flight has that same velocity. So if we've got a flight moving at, let's just say, 10 centimeters per second, then that could cause the water to have a 10 centimeter per second velocity as well. And would that 10 centimeter per second velocity dislodge the particles from the bottom of the tank and send them upwards? Well, that's what we're going to find out here. We're going to assume that we've got these particles where we know the density of the particle, and we know that we want to remove particles down to a size of 0.38 times 10 to the minus 7th meters. So these are relatively small particles, even smaller than the particles that were being removed in that exam question. You're given the liquid viscosity, but it doesn't come into play for this formula. we're going to assume kind of a middle value for beta, which remember was the parameter that describes how either sticky and interlocking or how independent and uninfluenced by other particles our particles are. So with a middle value of 0.05, what we're saying is some of the particles are interlocking, some of them are independent, but we're just kind of taking a moderate middle view. And the same idea here for the Darcy-Weisbach F value, that the friction factor of 0.025 is what we'll use for F here. So let's take a moment for you to calculate in centimeters per second what is the flight velocity that can be tolerated without scouring these particles in a negative way. All right, so we can move these flights at about 1 centimeter per second, and the particles won't be disturbed. So I guess that's reassuring, because that seems like a relatively, achievable velocity. I mean, if we were saying that it had to move at 0.1 millimeter per hour or something, it doesn't seem like we'd be able to control that, much less make it workable in a real-world situation. But 1 centimeter per second, with the right gears and the right motor, I'm sure that we'd be able to make that happen. And this is a relatively small diameter particle too. So if it was the particle that you were working on the exam, where it was like 1.2 times 10 to the minus fifth meters, then that would mean we could have an even higher scour velocity that could be tolerated. Now that doesn't mean that you have to move the flights at that velocity. It just means that that would be the maximum velocity that you could move it without disturbing it. So anything this or lower, and we won't be sending our settled sludge back up into the water. All right. Well, that's all I have for you today, unless there are any questions from the example. Maybe you saw my email that we've got some leftover food from the barbecue on Saturday. So if you want some Buddy's barbecue, it's over in the other building in room 109. We've got coleslaw, potato salad, chicken, buns, cookies. So help yourself.